Hey there, and welcome back to the deep dive. Get ready to plunge into, well, kind of the foundational layer of the digital world. Yeah, that hidden language that lets all your favorite apps, websites, and services actually talk to each other. We are doing a deep dive today into the absolutely fascinating world of API development. Now, the source material for this session is pretty incredible, actually. It's this really comprehensive guide distilled into 100 key insights. I mean, it covers the whole spectrum, from the fundamental concepts of what an API even is, all the way to the nitty-gritty of design, security, performance, and keeping them running smoothly over time. It's frankly a lot to navigate on your own.
And that's exactly what we're here for. Our mission really is to guide you through this detailed landscape. We want to pull out the most crucial insights, connect the dots between all the different facets of API development, and help you understand not just what these concepts are, but the vital why behind them. So whether you're directly involved in building software, integrating systems, or maybe you're just curious about the plumbing of the internet, this is your shortcut. It's about grasping the essential knowledge without getting totally lost in the complexity.
Okay, let's unpack this then. At its core, what are we even talking about when we say API, right?
So at its most basic, an API, or application programming interface, it's simply a defined way for two different software systems to interact. Think of it like a contract or maybe a set of rules. It specifies how one piece of software can request information or functionality from another.
Right, so instead of needing to know all the messy internal details of how another system works, like how its database is structured or what programming language it uses, you just need to know the API itself. The source uses a great analogy here, thinking of it like a menu in a restaurant.
Exactly. That's a perfect analogy. The menu tells you what you can order. Those are the available functions or data. And it tells you what you can expect to receive back. That's the response format. You don't need to go into the kitchen. The other software system to understand how they make your dish. The API abstracts away all that complexity, presenting a clean, usable interface.
And these aren't just one size fits all, are they? You see them used in different ways.
Correct. Yeah. You have public APIs, which are open for anyone to build integrations with. Think of like the Twitter API or the Stripe API. Then there are partner APIs shared only with specific business collaborators. And finally, private APIs, which are used internally within an organization to connect different systems or, different teams.
Got it. And the foundation for so much of this, especially on the web, is something we interact with constantly, without even thinking about it.
Absolutely. The vast majority of modern web APIs rely on the HTTP protocol. That's the same protocol your browser uses to request web pages. So understanding HTTP is really fundamental to understanding APIs.
Okay, so when we talk about building these web APIs, there are different philosophies, right? Different architectural styles for how you structure them. The most common one you hear about is REST.
REST? Yeah. Representational state transfer. It's incredibly popular, and for good reason. A core principle is that RESTful APIs are stateless.
Stateless.
It means each request from a client to the server must contain all the information needed to understand and process that request. The server doesn't rely on remembering previous interactions with that particular client.
Okay, so every request is completely self-contained, and REST uses those standard HTTP methods we mentioned as the way you interact with resources.
Precisely. In REST, you identify key resources, things like users, products, orders, whatever makes sense for your application. And each resource, or collection of resources, gets a unique identifier. Usually a URI, a Uniform Resource Identifier.
Like its address on the web.
Exactly. Think of it as its address.
So you might have users for the collection of all users, or maybe users 123 for one specific user.
Right. And then you use those HTTP methods to perform actions on those URIs. We often call these methods the verbs of the web.
Like get, post, put, patch, and delete.
Those ones. Exactly, those. You use get to retrieve data from a URI, post to create a new resource. Put is generally used to update or replace an entire resource. Patch H is for making partial updates. And delete? Well, that removes a resource. These are really the fundamental operations you perform on your resources via the API.
And after you send one of those requests, The API needs to tell you what happened. Did it work? Was there some kind of problem? That's where HTTP status codes come in, which are like crucial for communication.
Oh, absolutely essential. They give you immediate feedback on the outcome of your request. You'll see status codes in different classes or ranges. The 200 series codes, like 200 OK or 201 created, they indicate success. Everything went well.
Right, and then there are the 400 series for client-side issues, things the client did wrong.
Exactly, like 400 bad request if your request was just malformed somehow, or 401 unauthorized if you didn't provide credentials, like an API key, or maybe 403 forbidden if you did provide credentials. But you just don't have permission for that specific action.
And the classic 404 not found.
The universally recognized 404 not found. Yeah. If the URI you asked for simply doesn't exist. So these 400 codes are basically telling you, the client, that something is wrong with your request or your access rights.
Okay, and what if the problem's actually on the server side? Something broke over there?
That generally falls into the 500 series, like the infamous 500 internal server error. Why understanding these matters so much is this. If your API call fails, the status code is the very first place you look. It gives you a critical clue about what went wrong, and honestly, it can save you a ton of debugging time.
Okay, so assuming the server successfully processes a request and has data to return, it needs to send it back in a format both sides understand. What's the standard today? What about XML? You still see that sometimes.
Oh, hands down, it's JSON, JavaScript object notation. It's really become the lingua franca for data exchange and APIs. It's lightweight, super easy for machines to parse, and actually pretty easy for humans to read too. You do. XML is an older format you might still encounter, especially in, say, enterprise systems. But for modern web APIs, JSON is overwhelmingly the standard.
And how do the client and server agree on using JSON? Or maybe something else?
They use HTTP headers for that negotiation. The content type header tells the server the format of the data being sent in the request body, if there is one. And the accept header tells the server what data format the client is expecting to receive back in the response.
Ah, okay. So it's how they sort of agree on the language they're going to speak for that particular exchange.
Precisely. It's how they negotiate the format of the conversation.
So we've covered the basics of communication. Now let's think about structuring the API itself, how you organize those resources and URIs. There's some key design principles here, right?
Meaning you'd have users, not get users or create user. The HTTP method getPostPs already provides the verb, the action.
Makes total sense. Yeah, you're talking about the thing, the resource, not the action on the thing in the path itself.
Exactly. And structuring your URIs hierarchically helps show relationships. Like users 123 posts clearly suggests getting the posts that belong to user 123. You use parts of the path, like users 123, to identify specific resources or their relationships. Whereas query parameters, the stuff after the question mark, are typically used for things like filtering, sorting, or pagination, like posts, status, publish, and sort date.
And consistency across the whole API is really important too, I gather.
Crucially important, yes. Consistent naming conventions for endpoints, parameters, response fields, consistent use of plural nouns for collections, so books, not book, and consistent error formatting, which we'll come back to. Why does this matter so much? Well, consistency makes your API predictable. If a developer learns one part of your API, they can make pretty good educated guesses about how another part works because the patterns are the same. It drastically lowers the learning curve and reduces the effort needed to integrate with it.
Right, that makes sense. Now, APIs aren't static. They evolve. You add features, maybe change structures. How do you do that without breaking everyone who's already using your API? That seems tricky.
It is tricky, and that's where versioning comes in. You absolutely must plan for evolution and introduce versions to maintain backward compatibility. When you make significant changes, especially breaking changes, you release a new version.
What are the common ways to handle that versioning?
A very common method is URI versioning. You just put the version right in the path, like V1 resource or V2 resource. It's explicit. It's clear.
Okay.
Another option is using a custom HTTP header, like accept version, to specify the version the client wants. Less common, maybe, but cleaner URIs. Yeah, you also hear about semantic versioning.
Yeah, you also hear about semantic versioning.
Yeah, semantic versioning, that standard major, minor, patch XYZ numbering scheme, is often used alongside API versioning. It helps communicate the type of change. A major version bump X means breaking changes. A minor bump Y means new features, but backward compatible, and a patch bump Z is just for backward compatible bug fixes. Absolutely foundational. First off, ensure all communication uses HTTPS, period. This encrypts the data exchange between the client and server, protecting sensitive information like passwords or tokens from being intercepted over the network. Never, ever send credentials or sensitive data over plain, unencrypted HTTP.
Okay, now let's shift to maybe the most non-negotiable part, the absolute must-do, security. This came up multiple times in the source material, and, well, for obvious reasons. Okay, so encryption in transit is step one. Then you need to know who is making the requests to decide if they are allowed to do what they're asking. That's authentication, right?
Right, authentication is about verifying identity. Basic API keys offer a simple form, just a unique string the client sends, but they have limitations. They can be exposed. For more robust scenarios, especially when you're dealing with third-party applications accessing user data, OAuth 2.0 is the industry standard. It's a framework that uses tokens to grant delegated access without the user having to share their actual password with the third-party app.
Right, like when you sign into a service using your Google account.
Exactly that kind of flow. And JSON Web Tokens, or JWTs, often pronounced JWTs, are also very commonly used. They're a compact way to securely transmit information, often used to represent the authenticated user's identity and permissions after they've logged in.
And you have to check those credentials right at the very start of handling a request.
Absolutely. Enforce authentication and authorization checking permissions after identity is confirmed before you process any request logic, and a critical point mentioned more than once in the source. Never expose sensitive data. Don't put raw passwords, database connection strings, or internal system details in your API responses, especially not in error messages.
Right. And to protect your service itself, what about preventing abuse or just being overwhelmed by too much traffic?
That's where rate limiting comes in. You need to limit the number of requests a single client identified, maybe by their API key or IP address, can make within a specific time window. This prevents malicious attacks like denial of service, protects your backend infrastructure from overload, and ensures fair usage for all clients.
Makes sense.
It's also vital to store any secrets your API itself needs, like database passwords or API keys for other services it calls securely. Don't hardcode them in your application, use environment variables. Or better yet, dedicated secret management systems.
What else on the security front?
Well, regular security audits and penetration testing are essential to proactively find vulnerabilities, and you need to configure Core's cross-origin resource sharing carefully. This browser security mechanism controls which web domains are allowed to make requests to your API from a user's browser. Misconfiguring it can open you up to attacks.
Wow, okay, so why does all this matter so intensely?
Because it's not just about protecting your system's integrity. It's fundamentally about protecting the data and privacy of your users and maintaining the trust they place in your service. Security breaches destroy trust.
Absolutely. Okay, let's shift gears a bit. How do you make your API fast and responsive, especially when lots of people start using it? Performance and scalability.
Right? Because a slow API is a frustrating API. How do you handle increasing traffic and maybe large amounts of data? Techniques like caching are key. Storing frequently accessed data temporarily, maybe closer to the client or in an API gateway layer, so you don't have to hit your main database or backend service every single time. Using compression, like zip, can also significantly reduce the size of the data being sent back in responses, making them faster to transfer over the network.
And for resources that might have hundreds or thousands of items, like a list of products or posts, you can't just send them all back at once, surely.
Definitely not. That's where pagination becomes essential. You break large result sets into smaller, manageable pages. The client requests page 1, then page 2, and so on. Also, allowing clients to filter and sort results on the server side is crucial. This way, the server does the work and sends back only the specific data the client actually needs, reducing load and transfer size significantly.
And related to that is avoiding overfetching.
Yes, exactly. Don't return a massive data object with 50 fields if the client only needs, say, the name and the price. Some API styles like GraphQL, which we mentioned earlier, are designed specifically to solve this by letting the client specify exactly which fields they want back. But even in REST, you can sometimes offer ways to select fields.
And how do you know if your performance improvements are actually working? Or if your API can handle the expected load?
Load testing. You absolutely need to perform load testing to simulate realistic traffic levels and see how your API behaves under stress before you launch it or deploy major changes to production. Identify bottlenecks early.
Okay, now inevitably things will go wrong sometimes. Requests fail. How should an API communicate errors back to the client?
This is another area where a good API really shines in terms of developer experience. You must return clear, descriptive, and importantly, structured error responses. Instead of just sending back a generic 500 internal server error text, include details. Maybe a specific error code the client's code can check for, a human-readable message explaining the problem, and perhaps a details field with more specifics, like which input field failed validation.
And echoing that security point again, never leak internal implementation details in those errors.
Precisely. No Java stack traces, no database error messages revealing table names, no internal file paths. That kind of information gives attackers valuable clues about your system, and it's completely useless and confusing for the legitimate client developer trying to fix their integration.
So keep it informative but safe and consistent.
Absolutely. Just like the rest of your API design, error format should be consistent across all your endpoints. Use the same structure, the same field names for the error code and message. Why does this help? If error responses are clear, structured, and predictable, client applications can actually understand why a request failed. They can then handle it gracefully. Maybe display a specific user-friendly message to the end user. Or perhaps even attempt an automatic retry if it seems like a temporary issue.
Right. Makes the client developer's life much easier. But how do those developers even figure out how to use your API in the first place? What endpoints exist? What parameters do they take?
Documentation. It is absolutely the instruction manual for your API. Good documentation is simply non-negotiable if you want people to actually use your API successfully, and tools like Swagger and more broadly. The OpenAPI specification have become the standard way to define your API structure in a machine-readable format.
And these specs, these definitions, they could be used to automatically generate the documentation itself, right?
Exactly. Tools like Swagger UI or Redoc can read your OpenAPI specification file and automatically create beautiful interactive documentation. Developers can browse all the endpoints, see the parameters, view example requests and responses, and often even make test API calls directly in their browser from the documentation page. It's incredibly helpful.
So, what should good documentation always include?
It needs clear descriptions of all your endpoints and what they do, details on all required and optional parameters, including their data types, example request bodies, and example response bodies for both success and error cases. It should clearly state the authentication requirements. How does a developer get and use an API key or token? And it needs explanations of your specific error codes beyond just the standard HTTP status. Crucially, keep it updated. This sounds so simple, but it's often overlooked. Documentation must be kept in sync with every single release of your API. Outdated or incorrect docs are incredibly frustrating and basically useless.
Yeah, nothing worse. Speaking of making developers' lives easier, there are tools they use on their side as well when they're consuming or testing APIs.
Oh yeah, absolutely indispensable tools for anyone working with APIs day to day. For interactively testing and exploring APIs, you have fantastic graphical tools like Postman and Insomnia. They make it really easy to craft requests, send them, and inspect the responses in detail.
I've used Postman, it's great.
Yeah, they're lifesavers. And for automation, scripting, or just quick tests from the command line, the classic tool is curl. It's powerful and available everywhere.
And those open API specs we mentioned for documentation, they can help the client developer too, right? Not just for reading docs.
Yes, definitely. There are code generator tools that can read an open API specification and automatically generate client libraries, or SDK software development kits in various program languages like Python, Java, JavaScript, etc. This saves client developers a huge amount of time writing boilerplate code just to make basic API calls. They can just import the generated library and start using it.
Okay, circling back to those design principles we touched on earlier, if you had to summarize the overarching goals when designing an API, what would they be?
I think the primary goal above all else is to design for the consumer. Think about the developer who has to integrate with this thing. Make it easy for them to understand and use your API correctly. This means striving for an API that feels intuitive, predictable, and consistent, as we discussed. If you're building a REST API, really try to adhere to RESTful principles and leverage the standard HTTP semantics people already understand. Get for retrieval, post for creation, etc., and generally follow the principle of least surprise. Don't build something that behaves in a weird or unexpected way that goes against common conventions or developer expectations.
So make it hard to misuse.
Exactly. Make it hard for someone to misuse your API accidentally, and make it easy for them to understand how it works just by looking at the documentation or the endpoint structure itself.
Got it. Now, most of what we've discussed is the standard sort of request-response pattern, but the source also mentioned more advanced ways systems can communicate.
Right, not everything fits neatly into client asks, server answers. For real-time notifications, for example, you often use webhooks.
How do those work?
Instead of the client constantly pulling your API asking, "Is there anything new yet? Is there anything new yet?" Cool, your API makes a call out to an endpoint provided by the client when a specific event happens. Like when a new order is placed. This is much more efficient for getting real-time updates pushed to the client.
Okay, that makes sense for event. What about managing lots of different APIs within an organization?
That's where API gateways often come in, especially in microservices architectures or just complex systems. An API gateway acts as a single entry point for all clients. It receives the incoming requests and then routes them to the correct backend service or microservice. But it can also handle cross-cutting concerns centrally, things like authentication, rate limiting, logging, request transformation, caching. It simplifies the backend services and provides a consistent front door.
And if a single request coming into that gateway ends up bouncing through multiple internal services to get fulfilled, how do you possibly track what happened if something goes wrong deep inside?
Ah, good question. That's where correlation IDs are essential. The idea is you generate a unique ID for each incoming request, right at the edge, maybe in the API gateway. Then you pass that same ID along with every subsequent call made between internal services as part of processing that original request. So if there's an error, you can use that correlation idea to search your logs across all services and see the entire chain of events for that one request. Invaluable for debugging distributed systems.
Clever. What else in the advanced category?
Well, making sure you include important metadata in responses, especially for paginated lists, like not just the items on the current page, but the total number of items available, so the client knows how many pages there are. We also touched briefly on different interaction patterns beyond simple request response. There are asynchronous APIs, often using things like message queues or event streams useful for tasks that might take a long time to process. The client submits a job, gets an immediate, okay, we got it, response, like a 202 accepted status, and then maybe pulls another endpoint later or gets a webhook call when the job is done.
And for really real-time stuff like a chat app or livestock prices.
For truly real-time APIs, you're often looking at technologies like WebSockets, which provide a persistent two-way communication channel between the client and server, or server-sent events, SSE, which allow the server to push updates to the client over a long-lived connection. Sometimes pulling the client asking repeatedly is still used as a fallback if these newer technologies aren't supported or suitable.
Okay, so to ensure all this actually works reliably once it's built, testing and monitoring are absolutely essential, right?
You need different levels of testing throughout the development process. Unit tests check individual functions or small pieces of code in isolation. Integration tests ensure that different components or services work together correctly when connected. And contract tests are really important too. They verify that your API, the provider, and the clients using it still agree on the expected request and response structures of the contract. This helps prevent accidentally breaking clients when you change the API.
And once the API is live in production,
Then robust monitoring becomes critical. You need comprehensive logging of requests, responses, and especially errors. Track key performance metrics like request latency and error rates, and crucially, set up alerting systems based on those metrics and logs so your team gets notified immediately if something goes wrong, like error rates spiking or latency increasing significantly. You need to know about problems before your users do.
right, and how you actually deploy and manage your API over its lifetime matters too.
Definitely providing sandbox or staging environments is crucial. These are separate environments where developers using your API can test their integration safely without affecting real production data or systems. Using proper configuration management ensures that your API behaves consistently across different environments, development, staging, production, automated deployment pipelines, continuous integration. And continuous deployment, or CI/CD, mean you can release updates and bug fixes quickly, reliably, and with less manual effort.
And keeping users informed.
And keeping users informed. Maintaining clear change logs that document what's new or changed in each version is vital. And proactively communicating upcoming changes, especially deprecations or removals of endpoints, to your API consumers is key for good lifecycle management. Give them notice.
Makes sense. What about considerations specifically for the developers using your API, the client-side perspective?
Well, designing your API to support potentially various types of clients is important. A browser-based web app has different needs and constraints than a native mobile app or a server-side application, or maybe even an IoT device. Yep. We mentioned providing SDKs in popular programming languages that makes integration much easier for developers. They don't have to manually handle HTTP requests and JSON parsing as much.
And security from the client side.
Critically, never trust data coming from the client. Always perform thorough server-side input validation on any data submitted through the API. Check data types, lengths, formats, ranges. This protects against malicious inputs, malformed data, and potential security vulnerabilities like injection attacks. And for operations that absolutely should not happen more than once, even if the client sends the request multiple times due to a network issue like creating a financial charge. Implementing idempotency keys is a best practice. The client generates a unique key for the operation, sends it with the request. If they retry with the same key, the server recognizes it's seen that key before and can safely return the original result without performing the action again. Ensures reliability.
That ties back into managing the API's whole lifecycle, doesn't it? Planning for these kinds of things.
That ties back into managing the API's whole lifecycle, doesn't it? Planning for these kinds of things. As we discussed, versioning is the core mechanism, but you should also have a clear process for deprecation. Explicitly mark endpoints or features as deprecated before you remove them entirely. Give consumers ample notice, months, maybe even a year or more, for widely used APIs and provide clear migration paths to the new version or alternative.
And this versioning applies to the data structure too. Okay, we've covered a ton of ground. If we pull all these threads together, what are the core characteristics that make an API not just functional, but great?
Ultimately, I think it comes back to being designed with the consumer, the developer, using it firmly in mind. A great API has clear, consistent naming and formatting throughout. Its AM messages are actually helpful, easy to understand, and actionable. It often includes dedicated health check endpoints that monitoring systems can easily query to see if the API is up and running correctly. You could say a good API is hard to misuse accidentally and easy to understand quickly. Its structure, its documentation, they guide developers towards correct and efficient usage. And internally, it ideally should have a modular design. This makes it easier to maintain, test, and evolve individual parts without disrupting the whole system.
And it's not just about the API code itself, is it? The surrounding ecosystem matters too.
Oh, absolutely. APIs don't exist in a vacuum. They exist to enable integration between different systems, whether that's linking your company's CRM to an external analytics tool, or connecting an e-commerce platform to a third-party shipping provider. So, providing sample code, tutorials, and maybe even fully working example integrations can make it much faster and easier for developers to get started and see how to use your API effectively.
And fostering a community.
Yes, for public or partner APIs especially. Having a dedicated developer portal with all the documentation, guides, SDKs, and support channels is huge. Gathering feedback from the developer community using your API is invaluable for knowing what to improve. And using analytics to understand how your API is actually being used, which endpoints are popular, where errors are occurring, helps you prioritize future development. All critical for successful adoption and long-term health.
Wow, okay, we've really journeyed through this, haven't we? From the absolute definition of what an API even is, through the mechanics of how software talks, the principles of good design, the absolutely critical layers of security and performance, how to handle errors effectively, the huge importance of documentation, and even the ongoing life cycle of managing these essential building blocks of the modern digital world. It's incredible how much goes into making them work well.
It really is. And hopefully this gives you a shortcut to understanding that whole landscape, which, as you said, powers so much of our digital lives behind the scenes. Grasping these core principles is just fundamental if you're involved in building robust, usable, and scalable software in today's deeply interconnected world.
Yeah, the source material wraps up with a really great summary thought, 0.100 actually. Great API is well designed, secure, well documented, and evolves gracefully over time.
And that phrase, evolves gracefully. It leaves us with a fascinating question for you, the listener, to maybe mull over. Given that APIs are these unsung heroes, this essential infrastructure behind so many services you use every single day, booking a flight, ordering food, checking the weather, social media, what does that idea of graceful evolution actually mean for the future of those services we rely on? And how might our expectations as users need to adapt or evolve as the underlying APIs change and improve? Sometimes in ways we don't even directly see.
That's a great point to ponder. The next time you're using an app or a website, maybe just take a second to think about those hidden conversations happening beneath the surface. Think about the APIs making it all work and how some of the principles we talked about today, consistency, security, performance, error handling, might be shaping your actual experience. Well, thanks so much for joining us for this deep dive into the world of API development.